The invention of calculus is a long storied history, mostly revolving around the great controversy between Isaac Newton and Gottfried Wilhelm Leibniz, and who was the true inventor. Nowadays, the two are considered co inventors, as the two both developed calculus independently. Today, however, we will explore the role of Newton's teacher, a man essential to the invention of calculus but often gets glossed over. Let's take a look. Now, Isaac Newton was no doubt a genius, and perhaps still is the most influential man in science today. Newton developed loads of math and used it to describe and explain the natural world, something that had never been done before. His invention of calculus assisted his calculations and equations that could describe the natural world. But we actually see a lot of influence from his teacher, Isaac Barrow, in his calculus work. Barrow took 2 points on the curve where the distance apart was of infinite smallness and found the slope between the two, much like our modern definition of a derivative. He had methods for doing so for several different curves, some of which are shown here. Our focus today will be finding the derivative of this fun-looking curve here, first using Barrow's method, and then comparing it to our modern technique, implicit differentiation. To solve this, Barrow would have labeled the point that he wanted to find the derivative at. He then would connect it to another point close to it by what is called the differential triangle. The differential triangle had height A and length E. Now, since the other point is assumed to be on the line, we can just plug it into this equation. X plus E cubed plus y minus a cubed equals r times x plus e y minus a. X plus e cubed plus y minus a cubed equals r times x plus e times y minus a. Next, we should expand out this equation. This giant thing is our result from the expansion, but I want you to notice these three terms here. We have an x cubed and a y cubed on the left-hand side, and on the right-hand side, we have an rxy. Well, we said x cubed plus y cubed equals rxy, so these terms will actually all cancel each other out. Next, remember that a and e were the infinitely small distance between the 2 points. So, we have an e here, but this term has an e squared, so that's going to be infinitely smaller than this term here. So every term with a higher power than 1 of e or a, we can also cancel right out. So we're left with this equation right here. 3x squared e minus 3y squared a equals negative rxa plus rye. Now, what we're trying to solve is for the slope of this, which we know to be rise over run, or in this case, negative a over e. So let's get all the a's to one side and all the e's to the other side. Now, we can just factor out an e on the left and an a on the right. Notice I factored out a negative a because I said our slope was negative a over e. Well, now just by some simple rearranging, negative a over e is equal to 3x squared minus ry over rx minus 3y squared. There you go, that's our slope at any point on this line. Now, with this result in mind, we'll use our modern methods to solve it and see how it compares. To do implicit differentiation, the first step is to take the derivative with respect to x of both sides. So we take the derivative of x cubed plus y cubed, and then the derivative of rxy. For x cubed, it's pretty easy. It's just 3x squared regular power rule. Now for y cubed, we have to use the chain rule. So first we take the derivative with respect to y, which is 3y squared, and then multiply that by the derivative of y with respect to x, or just dy dx. On the right side, we have to use the product rule. I'll break it into an rx times a y, which ends up being rx times dy dx plus an ry. Now, we want to get dy dx by itself so that we can get the derivative. So we'll move all the terms with dy dx to the same side and all the other terms to the other side of the equation. After doing that, this is what we'll get. 3x squared minus ry equals rx times dy dx minus 3y squared dy dx. Now, as you probably guessed, we can just factor out the dy dx on this side of the equation. Last up, we can just divide off the rx minus 3y squared. And we'll get dy dx equals 3x squared minus ry over rx minus 3y squared, which happens to be the exact same as we got using Barrow's method. Barrow's method is quite useful because it actually explains what's going on geometrically, which we don't really see using the implicit differentiation. However, recall that our a and e were both set to be quantities of infinite smallness. Now, think about it. What does it even mean for something to be infinitely small? And how come we were just allowed to cross out the insignificant a squared and e squared terms? That's not something we normally do in math. Now, all these questions raised a lot of criticism in the practicality and legitimacy of calculus. In fact, it took about 100 more years before someone finally came along and provided some rigorous proofs on why we're actually allowed to make those moves. While Barrow's differential triangle was crucial to Newton's invention of calculus, it was not enough to be considered a full invention of calculus because he never generalized it beyond its geometric meaning. Newton and Leibniz were the ones to do so, publishing their work, which contained a full-fledged notation. That's it for now. Please consider liking and subscribing if you enjoyed. We'll see you in the next one.